There we go. All right. Welcome to Lecture 20. Man, there are, let's see, I think I did the math. There's 41 times that we as a class meet, so we're basically halfway there. Wow, I can't believe we're already halfway through the semester. It's kind of crazy. We got some headway on the homeworks. Homeworks 3.3 to 3.5 have been graded. The solutions posted. 3.6 was being graded. I checked this morning, and I think there were still some outstanding assignments, so that I don't think is still visible yet. But homework 3.7 is due today, and homework 4.1 is assigned. So that should tell you we're beginning sort of a new topic, a new module in the course. The module that we're beginning today, and admittedly this isn't coming out the greatest on this projector here. Let me check my little screen here to see if the text is a lot more legible here on the screen. My apologies. I have some later slides that are going to clarify this, but I'll explain what's going on here on this little table here today. Today we're beginning a topic assessing the equilibrium of rigid bodies, okay? So in particle statics, we sort of did all this in that second module altogether. So when we did particle statics, the first thing that we did is we just learned how to add vectors. And then the second step to that was, if I have a point subjected to a series of forces, what are the external unknown forces required to keep that particle in equilibrium? So the balloon problem is a perfect example of that. We had a particle that had a force applied to it. The balloon was yanking it up, right? And so what were the tensile forces in the three cables required to keep the particle in equilibrium? That was a static equilibrium problem. Now, that was a static equilibrium problem for a particle. So now what we need to do is static equilibrium of rigid bodies. So now not only are we dealing with the sum of forces being equal to zero, we have to consider the sum of moments being equal to zero. And usually the external forces required to keep the structure in equilibrium come in the form of what are called support reactions. This is a diagram showing a series of support conditions, and I'll illustrate some of these very particular support conditions later on in the lecture. But this is going to be kind of important throughout this topic, being able to recognize the support and understanding what are the unknown forces at that support condition. The other thing I'll mention in terms of logistics is, so today is Friday, October 8th. Today we're going to do equilibrium of rigid bodies. We've got 2 lectures devoted to equilibrium in 2 dimensions, and then 2 lectures devoted to equilibrium in 3 dimensions. So today and Monday we're going to do 2D, and then Wednesday and Friday we're going to do 3D. On Friday, October the 15th, we are going to have a pre-recorded lecture on YouTube. I'm not going to be here. In addition to being your statics professor, I'm also the associate dean, and we have our green and white day that Friday, so I'm going to be pretty busy that day. So I'm just going to pre-record that lecture. It is sort of a perfect lecture to pre-record because we're just going to be tidying up some things with 3D. And then Monday, we will have, the following Monday, which is the 18th, we'll have our second exam review. Then we'd have our second exam that Wednesday, the 20th. Everybody good? Okay. So let's talk about equilibrium, and I want to recall what we did before, and I want to explain how what we did before is different than what we're doing now. So, you know, the end of topic 3 was looking at equivalent systems of forces, and basically we state that 2 systems are equivalent if the sum of forces in system 1 equals the sum of forces in system 2, and the sum of moments in system 1 equals the sum of moments in system 2. So now I want to look at equilibrium. Now, with equivalent systems, we were concerned with just those 2 systems being equal. Now what I want to do is take it a step further, and I want to look at this little box right here. What I want to do is, for a given system, I want to set the sum of forces equal to 0, and I want to set the sum of moments equal to 0, okay? And by setting the sum of forces and the sum of moments equal to 0, I can use those expressions to determine the external forces required to keep the structure in equilibrium. Now, I'll go ahead and tell you, in 3D, that ends up being a pretty nasty problem that, honestly, even your Casio FX115 ES Pluses would have a hard time solving, because it would end up being 6 equations and 6 unknowns. So you know that your Casios and your equivalent scientific calculators and whatnot can solve 2x2 systems and 3x3 systems, right? So in 3D, they would be 6x6 systems. They'd be huge, right? So are we going to have some 3D problems in here? I will go ahead and tell you yes, but they are going to be structured in such a way that you are not going to have to do 6x6 matrix solutions, you know, by hand or in your calculator. They're going to be set up to where they're pretty easy to do by hand. Now, in 2 dimensions, we only have 3 equations, 3 unknowns, because we have the sum of forces in the x direction, the sum of forces in the y direction, and then the sum of moments. We say the sum of moments about the z-axis because, remember, if you're dealing in 2 dimensions, one of the things we learned about moments in 2D is that if you're dealing with forces and position vectors in 2 dimensions, that the moments are always generated about that 3rd axis. So there's really only 3 equations, 3 unknowns to deal with in 2D. Now, the other thing that's worth mentioning, and this is really going to become clear today, is that if you are creative and you are crafty with how you approach the problem, you can get by doing the problem without having to break out your 3x3 solver. You can use a little bit of your noggin and common sense and make the math a whole heck of a lot easier on yourself in 2D. But we'll get there. I need to talk a little bit about equilibrium and about the support conditions that keep the structure in equilibrium. So let's talk about boundary conditions. So this is sort of like my definition. I'm saying boundary conditions are supports that attach the structure to the ground. And I'm using quotation marks there with the ground because I kind of want to explain this. And they're the main components that keep the structure, the main force components that keep the structure in equilibrium. Okay? So I'll give you a couple of examples so that you can kind of understand what I'm talking about. The first example is what's illustrated here in this image. Does everybody recognize this? I would think you should, right? This is the canopy that connects the older engineering building to the new engineering building on the other side of 3rd Avenue. And so, for example, the boundary conditions for some of these elements are going to behave a little differently. For example, if I look at this beam right here, this beam on top, and you can see this little arrow I have pointing here, one of the things you'll recognize maybe after today is that I would consider this beam to be connected to the column using what I'll call a simple support. And a simple support is basically just one that only transmits forces. It doesn't transmit moments. Whereas if I'm looking at this column, and I'm looking at this column that's been embedded into the concrete below here, I'm stating that that connection is able to resist not just forces but moments as well. So whereas this might be a simple support, this might be a fixed support. Now, the other thing in terms of the ground is that, you know, for example, if I'm looking at this column, the boundary condition for this column might be like right here on the ground. But for this beam is not connected to this ground. The beam is connected to this adjacent element. So the ground can be the next adjacent component, right? So if you're designing, you know, like a building, beams frame into girders, girders frame into columns, columns frame into ground. When you're looking at the beam, the support conditions are just the next adjacent elements that the component is connecting to. And you can use that logic whether or not you're designing a building, whether you're designing, I don't know, a car frame, and you're looking at a given element in the frame. You might, you know, the ground might just be the forces going into the next adjacent component. If you're looking at the stresses, I don't know, for you biomedical engineers, if you're looking at let's say a plate that you're affixing to somebody's arm, you know, maybe the ground is, you know, their next linkage in their arm or their elbow or something like that. So you can still use those analogies to determine the forces. And this process of taking a system and ultimately determining the external support reactions required to keep the structure in equilibrium, but B, also the internal forces developed inside the system. We have a name for that, and we call that structural analysis. And so that is going to be one of the tasks that we try and start to attack near the end of the semester. For you civil engineers, we have a whole course dedicated to structural analysis because that's one thing civil engineers do is they design structures. So, okay. Any questions so far about the concepts? Okay. Now, one of the things that I get across on day one when I teach structural analysis, which I'm teaching this semester as well on top of this, is I say, look, one of the concepts you got to get through in your head is that we're actually not analyzing structures. We're analyzing mathematical models that represent structures. And so those mathematical models have rules, and we need to understand what those rules are in order to understand the overall behavior and the resulting reactions that we need to solve for. And so within those rules of mathematical models, we have a series of common support conditions that we use to idealize rigid bodies and systems. And so I want to go through some of the ones that are the most common. And I'm going through them not just because they're ones that we're going to be experiencing here in this course, but they do have idealizations in real life. For example, one of the most common support conditions is what's called a pinned support, okay? One of the most common images that I would use to draw a pinned support is a triangle, okay? This is sort of my shorthand symbol for a triangular, or for a pinned support. Pinned supports, and to be clear, my discussion today is focusing only on two dimensions. I propose that any time I draw a pinned support, that they have two unknown reactions, an unknown reaction in the x direction and an unknown reaction in the y direction. And so whenever we're assessing rigid body equilibrium, one of the first tasks is to identify the reactions, identify the unknown reactions, and then develop a strategy for solving for those reactions. Okay? And so I propose pinned supports have two unknown reactions, an unknown reaction in the x direction and an unknown reaction in the y direction, and they are independent of one another. Now, one of the things about a pinned support is that it does prevent translation. Okay? I cannot take this element and move it this way or move it this way. It is prevented from translating. However, if you just look at this support would allow free rotation of that member, right? So one thing you will not see at a pinned support is an unknown moment reaction, okay? And to show you a little bit of an example later, I'm skipping a couple of slides, but when we look at fixed supports have an unknown reaction in the x direction, an unknown reaction in the y direction, and an unknown bending moment, okay? So we can see that with different support conditions. And so I propose that this is an example of a pinned support. Now, one other example of a pinned support, which you might be looking at this and go, wait a minute, you're telling me this is a pinned support? Because I see 3 bolts going through that I-beam over here. Wouldn't that, wait a minute, wouldn't that restrict rotation? I guess yes, if you're thinking about it from just a simple motion standpoint, but right now you're in statics. Next semester you're going to take a course called Mechanics of Deformable Bodies. The current plan is I'm planning on teaching that course next semester as well. And one of the things you'll learn about is we take what we learn in here and we go one step further. We look at the internal stresses and strains that get developed in members if you bend them or twist them or shear them or stretch them, and then how much do they deform, how much do they strain, and so on and so forth. And so what you find in I-beams, how many of y'all have ever seen or heard of an I-beam before? The reason that I-beams are configured the way they are is because whenever you're trying to design that shape, the idea is to get as much material away from the center of gravity or the centroid of that I shape as possible, which is why you have a beam and you've got 2 plates that are sort of way far out in space. So the idea from a mechanics of materials perspective or mechanics of deformable bodies perspective is that the flanges, do y'all know what I mean by flanges? If you have an I-beam, the top and bottom plates are the flanges, and the middle plate is what's called the web, okay? The idea is that for an I-beam, the flanges carry the a significant component of the moment, but the web is what carries the shear or the vertical forces. So since this connection is only transmitting those shears and not those moments, we would idealize that as a pinned support. Does that idea kind of make sense? So Whenever you see like a steel frame building, if the flanges are connected, that'll transmit moment. If not, it'll only transmit forces. Okay, another common example of a boundary condition is what I call roller support. Roller support only restricts motion in the direction of the roller, okay? Now, I have here that the reaction is going upward, but analytically, again, from our mathematical modeling perspective, the reaction could be upwards or downwards, okay? And some of you might think, wait a minute, how would the reaction be downwards? A common example of that would be the diving board concept. So here's a person on a diving board. They are applying a load downward. And so think, how does that roller, if this is the roller, how does it have to behave to keep the system in equilibrium? It has to pull down as well, right? Because if not, if I'm standing on the end of that diving board and that roller isn't holding it back, I'm going to go for a tumble, right? I don't want to go for a tumble. This is statics. We want to keep things stable, right? Does that make sense? Okay, so roller supports are some of the most common boundary conditions that we see. Together with pin supports, a very common scenario that we see in analysis, and this is true in civil engineering, mechanical engineering, any type of engineering, even biomedical, any engineering field that deals with solid mechanics, taking objects and putting forces on it and ensuring that they're going to hold up. A common support condition scenario is something like this, where we have a hinge support on one side and a roller support on another. This is a very, very common boundary condition scenario. We have a name for this. We call this simply supported. This is very common, okay? I'll give you a real-world example, all right? This is very common in bridge applications. I know I'm a civil engineer, and some of you are getting sick and tired of hearing about bridges, but I don't care. I'm a bridge engineer, and by God, you will learn something about bridges. So one of the things that we do in bridge engineering is we use what are called fixed and expansion bearings, right? So on one end, the device that connects the bridge to the abutment will be fixed, and on one end it will allow expansion. Typically, the way that we do that is we'll use plates with bolt holes that are either circular or on the other end, bolt holes that are slotted that allow a little bit of translation. Now, why would you want that? Why would you want your bridge to move a little bit left and right? The answer is temperature, okay? So I don't know about you, but I remember this summer we had some days in this area of the country we were starting to hit 90, maybe triple degree weather, right? Now, what about February? Does anybody remember the ice storm to end all ice storms, right? The Westeros winter is coming, storm that we had that knocked out power and so on and so forth. Those were some pretty cold days, right? Well, those bridges have been outside in those environments, and so they've experienced plus and minus temperature changes of like 100 degrees, right? Between 100 degrees to maybe like 0 degrees. That bridge will undergo thermal expansion and contraction. So allowing the bridge to move a little bit is actually a good thing, because let me tell you, if you restrict that, you can get some serious stresses due to restriction of thermal expansion and contraction, and something we will talk about in Engineering 216. Okay, this is a fixed support. Fixed supports restrict both motion, they restrict motion, so they restrict both translation and rotation. So whenever in two dimensions, whenever you look at a fixed support boundary condition like this, you're going to see unknown reactions in both the x and y direction as well as an unknown bending moment. So whenever you see a fixed support, there are 3 unknown reactions, okay? And here's a couple of examples of this. So if you look at like this is connecting both the flanges and the web of that I shape. So that connection would transmit moment and forces. So yes, that would be a fixed support. Just like the column that's embedded in the concrete, embed it deep enough, and that connection is going to be able to resist both forces and moments. Does that make sense? Everybody okay with that? All right. So here's a summary of some of the boundary conditions that we're going to be dealing with. And our first task is going to be to determine external support reactions. So what we're going to be looking at are systems with 3 equations and 3 unknowns, okay? And I'm going to make a few comments about that here in a little bit. But 3 equations and 3 unknowns probably gets you thinking about that 3x3 solver in your Casio FX115ES Plus or similar device. And what I'm saying is that if you're strategic and a little crafty about how you do this, you do not need to break out that solver, okay? You can make your life a lot easier by not having to do that, and you'll understand that as we get into the system, okay? So our first problem is going to be this. This is a very, very simple problem. We have a system. This is a beam. This is a simply supported beam. We have a pin support here and a roller support here. And we have a series of applied vertical loads, and we are to determine the reactions required to keep this beam in equilibrium, okay? We're going to have another problem here in a bit that's a little bit more involved, but not really. It's going to be something very, very similar. Let me go ahead. Let's start getting into this, okay? Let me hit escape. It's going to ask me about those ink annotations that I want to discard. I'm getting wise to this. Okay. So here's the problem. Now, I want to make a couple points about how to address this, okay? First off, okay, how many unknown reactions are at B? So see, people have been paying attention. At support B, how many unknown reactions do we have? B is a roller support right here. 1. There you go. 1 reaction. Now, before we start taking the supported A, let me ask you a question. I've got a bunch of loads acting downward. Which way do you think that B is acting to keep the structure in equilibrium? Up. Okay? All right. So here's what we're going to do. I am going to assume that B is acting upwards. So we're going to call this BY. And I usually draw a little line through my reactions to indicate that I didn't know those at the beginning of the problem. Now here's the thing. Let's say that I go through all of the math and I get that BY is negative. What that means, well, what it doesn't mean is that I don't need to develop significant emotional distress about the problem. All it means is that I assumed that BY is upward and I get a negative answer. It just means that BY is acting downward. Right? If you have a force and a line of action and the magnitude is negative, it's just other way on that line of action. Make sense? Okay. Now, support condition A, okay? This is a pin support. How many unknown reactions are at support A? 2. All right, so what I will do is make similar assumptions, okay? We'll call this AY, and we'll call this AX. Now, I'm sure there's a couple of you are in here thinking, wait a minute, what's going on with AX? There's no horizontal loads. Don't worry. We'll get there. All right. Everybody with me so far? Now, there are how many unknown forces? 3. Okay. There are 3 unknown forces. I propose that we have 3 equations of equilibrium. The sum of forces in the x direction must be 0. The sum of forces in the y direction must be 0. And to keep it simple, I'm just going to say the sum of moments must be 0. Okay. How many equations do I have? 3. How many unknowns do I have? 3, right? Okay? There is a name for when that happens, okay? whenever the number of equations match the number of unknowns, that system is statically determinate, okay? I'll write that out, statically determinate. So my point is, and you don't need to write this, don't write this, but what if I put a roller right there? If I put a roller right there, I would get another vertical reaction, right? Then there would be 4 reactions. There would be 4 reactions, and there would only be 3 equations of equilibrium. There would be 1 too many unknowns, right? If there were 1 too many unknowns, that system would be statically indeterminate. I will not give you an indeterminate problem in this course, period, okay? The reason why is because, well, let me put it like this. Do engineers have to deal with indeterminate systems? Yeah. How do you handle indeterminate systems? You need to know Engineering 216. So we'll get there later, okay? Make sense? All right. Likewise, what would happen if I removed one of these reactions? Let's say BY. Let's say I kicked out BY. I'd have more equations than unknowns, right? But there is a simple name. If I took that beam and I kicked out the roller at B, that beam would be unstable. I will not give you an unstable problem either, okay? This is statics. This is not dynamics. Okay. Now, I am going to utilize these 3 equations of equilibrium to develop 3 equations to solve. And I am going to start with the middle one. We're going to start off with the sum of forces in the y direction equals 0. Now, when you write these equations, you have to pick a sign convention. You have to pick something and go with it at the beginning. So what I'm going to do is I'm going to pick that forces acting upwards are positive. I could pick forces downward are positive. It doesn't matter. Because ultimately what I'm saying is that everything going up has to equal everything going down. So it doesn't matter if I say upwards positive or downwards positive. I'm just picking something and go with it. So let's go through this. AY is going up. What about that 20 kips? It's going down. The 30 kips, going down. 18, going down. BY is going up. Do I consider AX in this expression? No, I'm writing sum of forces in the y direction. Did I miss any? No, right? That's all of them, right? AY, 20, 30, 10, 18. And so this sum must be equal to 0. And what I can do is simplify this a bit. Take the 20, the 30, the 18. What is 20 and 30? That's 50, 18, 68. Move it all over to one side, and I get AY plus BY has to equal 68 kips. I'm going to call this equation 1. Is everybody okay with that? So I don't know what AY is, I don't know what BY is, but AY plus BY has got to be 68 kips. I know that. So far, so good? Now, I dealt with sum of forces in the y direction. What about sum of forces in the x direction? Let's put that right here. And for the sake of discussion, let's take forces to the right as positive. What do the sum of forces in the x direction equals to 0? What does that expression tell me about this system? A sub x is 0. That's it. So that's actually one of our answers. This is one of our answers right here. At the beginning of the problem, it was unknown. But since the sum of forces in the x direction equals 0, and there are no other loads acting to the left or right, that reaction must be 0. Is that okay? Now let's deal with the third expression, the sum of moments. Now, this is where I had mentioned that it is good to be crafty, okay? I have an expression here with two unknowns, okay? Now, here's the thing about sum of moments. We are going to be writing a mathematical expression that quantifies the sum of moments on this system. The beam doesn't care where we sum moments. We could sum moments about any point. We could sum moments about this point or that point or this point or that point. We could sum moments over here, over here. It doesn't care. That doesn't mean we need to make our life difficult. What we can do is be crafty about where we sum moments. Now, if I have a point, and I have a force going right through that point, how much moment is being generated about that point? 0. That's exactly right. So what I propose is that we sum moments about A. Now we could sum moments about B too. I'm just starting at the left, working my way over. Now, when we sum moments, let me scroll down a little bit. When we sum moments, we do need to, again, pick a direction. What I am going to do is say counterclockwise moments are positive. There is absolutely nothing wrong with saying clockwise moments are positive. I don't care which one you do. You can do whichever one you want. Most textbooks, I think, typically go with counterclockwise positive because you're going from positive x to positive y, but it doesn't matter. Okay. Let's start. So whenever you sum moments about a particular point for a problem like this, what you're doing is you're keeping your eye, right, there's your eyelashes. You're keeping your eye, you're like, what is he drawing? You're keeping your eye fixed on this point, okay, and quantifying the moments generated by each of these forces. Let's start off with the 20 kips, okay? Let me ask you a question. Let's make sure we're paying attention. The 20 kips, does it generate moment about point A? In other words, does that want to cause point A to rotate? Yes. Which direction? If you're looking at point A, what does that 20 kips want to do? Does it want to rotate point A clockwise or counterclockwise? Clockwise. So does that mean it's a positive moment or a negative moment? Negative. Now, what's the moment arm? What is the shortest perpendicular distance between the line of action of 20 kips and A? 6 feet. There you go. See, this isn't so bad. All right. So there's the 20 kips. We handled that. What about the 30 kips? Does it generate moment about point A? Yes. All right. Positive or negative? Now, how far is it from A? 15 feet. So we say minus 30 kips, 15 feet. What about the 18? What is the moment arm from A? 22, exactly, because from A, that is the moment, force times distance, FD, right? Now, what about BY? Is it generating moment about A? Yes. Positive or negative? Positive. There you go. What's the moment arm? There you go. Now, did I forget something? What about AX and AY? They don't contribute moment because the moment arm is 0. So sum all that up equals to 0. How many unknowns do I have in this expression? Just one. No need to break out the Casio FX115 ES Plus. Just write it out. So 20 times 6, 30 times 15, okay, 18 times 22, I'm going to have to look that one up, 396. Okay. All right. 120, 450, and 396, that's what? 966? So in order to solve for BY, what do I need to do? Add and divide. So BY is 966 foot kips over 30 feet. What is BY? Now, did we get a positive answer? Yes. So this is how I'm going to write it. I'm going to say that BY is positive 32.2 kips, which means 32.2 kips upwards. In other words, at the very beginning of the problem, I assumed that that reaction was acting upwards. And I got a positive answer, which means that my assumption was valid. Okay? If I got a negative answer, that's okay. It just means that my assumption's wrong. What's left? What did I forget? AY. But how do I do AY? There you go. Plug it into here. So I'll scroll down a little bit. Somebody in there is probably like, Dr. Mike, will you just draw your Y's the same way? Like there's this, and then there's that. Just pick something and go with it. So what's AY? I heard a couple people say that. Positive? There you go. And so on these problems, it is conventional to just say, look, here are the answers. What are the answers? AX is 0. AY is 35.8 kips going up. BY is 32.2 kips going up. That's the answer. And notice how each of these reactions are forces. And how do you define a force? With a magnitude and a direction. Magnitude, direction. Magnitude, direction. That's 0, so it doesn't matter what the direction is. I don't care at the end whether or not the value is positive or negative, because the positive or negative determination is just based on your assumption. What matters in the end is the direction, okay? Because what if I assumed these reactions were downward? I got negative 35.8. But a downward reaction of negative 35.8 is just an upward reaction of 35.8. This removes the context of your assumption and just gives the real deal answer. Does that make sense? How are we feeling about this? Everybody good? This isn't so bad, is it? Gets us out of 3D land. All right, any questions? All right, let me show you. We probably won't finish this problem, but that's okay. I have a problem here that looks crazier. It really isn't. All right, so we could probably knock this one out pretty quickly. So I have a fixed crane that has a mass of 1,000 kilograms, and it's used to lift a 2,400 kilogram box. Right off the bat, I'm like, I don't like that. So that's 9,810 newtons, or 9.81 kilonewtons. Just like with this one right here. All right, this equals, I'll do this one for you, 23,544 newtons. 23.544 kilonewtons. Already, right off the bat, convert. Okay, so we have a crane that has a center of gravity right here, so we can assume that the weight of the crane is acting right here, and we have a 2,400 kilogram weight being applied at this point here at the top, okay? And so the idea is, what are the support reactions required to keep the crane in equilibrium, okay? So from a free body diagram perspective, this problem might look a little weirder. It's really not, okay? First off, here's the crane. We'll draw it sort of like this. So this force right here is 23.544 kilonewtons. And then there is a force that's like right here, that's 9.81 kilonewtons. And to be honest, I've got this crane and it looks like this truss. It doesn't really matter what the truss looks like for the sake of the problem. Later on, it very much will matter what that truss looks like, because we're going to learn how to determine the internal forces inside those truss members. But in terms of my boundary conditions, I have a support condition here at A, and I have a roller condition at B, okay? And in terms of distances and directions, so we know that this dimension here is 1.5 meters. We know that this dimension here and this dimension here are 2 meters and 4 meters respectively. And in terms of our reactions, how many unknown reactions do we have right here? 1. How many here? 2. So here's what I'm going to do. I'm going to say that my vertical reaction here is acting upwards. So we'll call this AY. And here's the thing. I know it's tempting to look at this problem and say that there are no horizontal loads. So if there's no horizontal loads, there are no horizontal reactions. That is not true. What I propose is that there are always unknown reactions, and you let the equations of statics figure it out. because there are unknown reactions in this problem that are horizontal. And if you want, you can assume them both to go like this and go like this for the purposes of analysis. And watch this. If you don't believe me about the horizontal reactions, let me ask you this. If I sum moments about point A, I'm going to have this force contributing moment and this force contributing moment. If I didn't have this horizontal reaction here, there'd be nothing to counteract that moment in the opposite direction. The sum of moments must be equal to 0. Does that make sense? So there's got to be something there. All right? Now, this is what I'm going to do for this problem. Instead of doing this problem, I'm going to give you the answers. And I think that you ought to have this problem in your back pocket as something to go off of, to check and see if you understand this concept. I propose that when you finish this problem, you're going to get AX is 107.26 kilonewtons going this way. It actually goes left. So when you solve forces in the x direction, I mean, what are you going to get? AX plus BX is 0. So that means that AX has to be negative BX. So they're going to be opposite signs. So AX is going like that. BX is 107.26 kilonewtons going this way. And as for AY ends up being 33.544 kilonewtons going up. Now, here's the thing. I think that AY should be pretty easy to determine. What would be a simple way of figuring AY? I mean, some forces in the y direction. What do you have? You got that down, that up. So what's this plus this? It's that, right? This isn't that difficult, okay? Hopefully you see that. What do you think? Does anybody have any questions about this? Oh, I thought you had a question. On the statics attendance sheet, Luke Skywalker signed in on Wednesday, so I'm curious to see who signed in today. That's all I have, everybody. You all have a wonderful weekend. We will see you all on Monday.